So now that you know how to find the equation for a derivative of an implicitly defined equation, we're actually going to put this to work. Remember, the whole point of finding the derivative is because we really care about a tangent line. And even though these things aren't functions, they do have tangent lines. So this is a much more realistic use of the skill you just learned. The instructions say to find the equation of a line that's tangent to each curve. Remind me again, what is your answer going to look like? Exactly. Probably point-slope form, although slope-intercept form wouldn't be wrong. And then look at what they've given us. They've given us an implicitly defined equation and a point. So we really just need one thing. We need the slope. Now, for this first one, I'm actually going to cheat ever so slightly because back in the examples from the last slide, you've already worked out an equation for the derivative. If you remember, it was the first one that you did. And it turned out that the derivative of this function was y prime equals x over y. Normally, I would have to stop and work out the derivative again. Since I already know what it is, I'm just going to start from there. And since I know an equation for the derivative, I'm going to use this equation to find the slope at 3, negative 4. All that means is just plugging in x and y into this equation. And that gives me a y prime of 3 over 4, and that's the slope of the original equation, which means it's now really easy to write the equation of a tangent line because I have a slope and a point. We just plug into point-slope form and double check that you flip your sign. One way to confirm that this is right would be to think about the graph. So if you remember, what is this shape going to be? Yeah, exactly. That's going to be a circle. And it's a circle with a radius of 5. Here's the circle from earlier. So if we want to just check that our derivative is working for us, I would go to this point, 3, negative 4. So let me add a point here. And then I'm going to add a tangent line. And I'm going to look at the slope when we reach that point. So I'm going to move along my curve all the way over here until I reach the point, which is approximately at 3, negative 4. And then looking at the slope of the tangent line, I should see that it looks like it's negative 3 over 4. Now, it looks like we did something wrong because this is a positive slope. And actually, when I look back at my original work, I found the typo. There was a negative right here, which should have left me with a slope, a derivative of negative x over y. And if I correct that error here, I end up with a positive 3 over 4 slope. And that confirms. If I look at the tangent line, the slope of this tangent line is up 3 over 4. That line looks just about perfect. Okay, now, hopefully you don't make mistakes in the first place, and you don't need to use Desmos for all of these examples. It's just giving you an idea of what we're doing. This second graph is not something I'm going to visualize. We'll just do the work out. Unfortunately, unlike last time, I don't know what the derivative is, so I'm going to start by finding what the derivative is. And since this is an implicit equation, and that's because we've got x's and y's together in the equation, not isolated, I'm going to find the derivative implicitly. That means take the derivative of each side and treat y as a function of x. Let's look at the left side first. When I go to take the derivative of x times sine of 2y, I'm going to recognize first of all that there's a product rule, and inside of the product rule there's going to be a chain rule. So I start with the bigger structure. The overall structure here is that we're multiplying two things together. To take the derivative of that, I'm going to do u times dv, which is x times the derivative of sine of 2y. I know the derivative of sine is cosine, but since there's a 2y on the inside, this is where the chain rule comes into effect, because the derivative of sine of 2y, which is my dv, is the derivative of the outside, which is cosine, with the inside function plugged in, which is 2y, times the derivative of the inside. And the derivative of 2y is 2 times y prime. Remember, that's because y is actually a function. If I take the derivative of x, which I'm about to do, it's just going to disappear. But the derivative of y is y prime, and the constant rule just keeps the 2 out front. This is u times dv. Now I need to add v, which is sine of 2y, times du, which is just 1. And that turns out to be my left-hand side. Next up, we look at the right-hand side. On the right-hand side, we again have a product rule where one of our two products is also going to have a chain rule. So we start u times dv. Why did I write a 2 right here? Exactly, because that's the chain rule. We take the derivative of the outside, which is cosine, keep the inside, but take the derivative of it at the back. Now, this was u times dv, and then I need to add v times du, and that's just y prime. Great, so I've taken the derivative of both sides. What's my next step? Exactly, I'm going to gather the terms with y prime so that they're together on one side of the expression. For me, that means I'm going to keep this expression and this expression on the left, and then the sine of 2y is going to move over here to the right. There we go, and notice that they change sign because they move over. Technically, I subtracted on both sides. I also switched up the order a little bit here so that I can see easily now that I'm going to take out a GCF, which is going to be a y prime. And now all I need to do to get the derivative by itself is divide both sides by this expression right here in parentheses. And I get my final derivative, which is this nasty looking fraction right here. And from there, we really need to just think about the goal, which was to write the equation for a line. So even if this is an ugly looking derivative, all I'm going to do is plug in x and y to find the slope of the tangent line. At the point pi over 4 pi over 2, the derivative, y prime, is going to equal, and then we evaluate. I recommend evaluating the sines and cosines first in your head because sometimes they'll just turn into ones and zeros. For example, when I look right here, sine of pi over 2. Well, 2 times pi over 2, the 2's cancel out, and I just get sine of pi. And I know that sine of pi is actually just 0. So I'm going to remember that this one's going to turn into a 0. At the same time right here, sine of 2 times pi over 4, well, 2 and 4 simplify, and this becomes pi over 2. Sine of pi over 2, think about the unit circle, is going to be a positive 1. And then down here on the bottom, cosine of pi, right, because those cancel out. Cosine of pi is negative 1. And cosine of pi over 2, when we simplify in here, is going to be 0. So we evaluate. We get pi times 1 minus 0 over pi over 2 times negative 1 minus 0. The zeros go away, and then we keep change flip, and amazingly enough end up with this really simple looking slope. Last step is to put it all together into the equation of a line, and that's what your answer is. All right, try this process. You've got 2 for yourself. Excellent. Here's the answer to the first one. Pause if you need more time. And here's how I worked out the second one. And as you can see here, I was using a product rule with the x squared and the cosine squared of y. And this is all supposed to be the first line of work with the 0 on the other side. Great, so I'd like to end this video just by wrapping up a couple loose ends. If you've been paying attention, we've been using a bunch of different derivatives, and out of all the ones we've been using, I've by now proven all of them to you using derivative rules, except for these two, the e to the x and the ln of x. So now that you know how to do implicit differentiation, I can actually prove to you that the derivative of the natural logarithm is 1 over x. Before, you just had to kind of believe me based on the graph, and we used the Ender function, and it was convincing, but it wasn't really proof. Well, now I can prove it to you. To start with, I'm going to prove why the derivative of e to the x is itself. It's this weird thing where the derivative doesn't change the function. And I'm going to prove it just using the limit definition. If you struggled with the question 4 on your quiz, this process is exactly the process you need to be practicing. Just like all the other proofs, we start with the definition of a derivative. By definition, the derivative of a function is the limit of the difference quotient. The meaning of the difference quotient is the slope at a point x, just at that point. It's the limit of a bunch of secant lines. So this expression represents the slope of a secant line, whereas when we take the limit, this is the instantaneous slope or the slope at a tangent. When we plug in e to the x, our expression looks like this. And if I were asked to justify what I've done so far, I would say, well, this is true by the definition of the derivative. Next step, I'm going to use some algebraic techniques to simplify. And out of respect to your time, I'm not going to work through it step by step, but you can see the work, and hopefully these are all steps that basically you're capable of processing, and you should be convinced, indeed, the derivative of e to the x is itself. Now that we've shown this conclusively, we can add the derivative to our repertoire of derivative tricks, and we can use it as part of the chain rule and product rule, which, to be honest, we've already been doing. More importantly, though, I can now use this to prove the derivative of the natural log, and this is where we use implicit differentiation. This is the fun part. This proof we're going to start a little bit differently than the last one. We're actually going to start with a fact from Algebra 2. So we know I want to talk about the function ln of x. Instead of setting up the derivative with the derivative formula, let's just look at this function for a second. When we say the function ln of x, we could write y equals ln of x. Or we could write f of x equals ln of x, but basically we're just saying there's an input and an output. There's my input, there's my output. Well, in Algebra 2, you learned that there's actually a better way to write this. And I'll take an intermediate step, which is to remember that the natural log is actually just shorthand for log base e. And when I think about it as log base e of x, this equation is basically asking a question. It's saying e to what power equals x. That's what a logarithm is. Or in other words, you could say this expression means that e to the y power equals x. Let me write that out. So these two equations are equivalent. They mean exactly the same thing. In this one, y is by itself. In this one, x is by itself. So our goal is to take the derivative to find y prime. But we don't know what the derivative of ln of x is. So I'm going to take the derivative of this equation. And it's an implicitly defined equation because y is not by itself. But it's easy enough to take the derivative of this because I do know about e to the y. And so implicit differentiation says take the derivative of both sides. Well, the derivative of x is pretty easy. That's just going to be a 1 on this side. And on this side, the derivative of e to the y, this is technically a chain rule. My outside function is e to the y. The derivative of that is just e to the y. And then I have to multiply it times the derivative of the inside function, which is y prime. And now my goal is to get y prime by itself, which just means dividing both sides by e to the y. And I realize that y prime equals 1 over e to the y. And then I'm going to do something really sneaky, which is I'm going to direct you back up to the top because there's another way to write e to the y. E to the y is the same thing as x. So if I just make that replacement, because they have to equal each other, I've just shown you that the derivative of this function is 1 over x. Boom, done, beautiful. All right, I'll end here. Good work with the implicit stuff. We'll pick back up in class.